So this is my presentation over 3D printing antennas and other dark arts. And so I am a spacecraft radio frequency engineer at Boulder Aerospace here in Colorado. Originally, I started out with them doing antenna design engineering on their aerospace defense side. I graduated May of last year with a degree in electrical engineering. Took a few antenna design, passive microwave design, and radio frequency courses. I was lucky enough to have Ham as my RF lab professor. I think he'd been a ham since he was about 12 years old. One of those people that has RF magic in his fingers and could fix just about anything RF, any circuitry that you can imagine. I'm not terribly active with the ham radio community. I'm not particularly fond of talking to people. I like the building part of things. So I've been a ham since 2015. I got started by building a repeater at a Martian analog site. That's where you go out into the desert and pretend to be an astronaut on Mars. And I was helping them resolve some of their communication issues. Done a field day, built a receiver, did a few Yagis for that RF lab professor that I mentioned. This horn antenna that's pictured here is the Ewan Purcell horn at the Green Bank Observatory in West Virginia. So that was kind of a neat thing to see if you're ever out in that area. There's lots of big antennas out there. So one thing I will say, I know everyone here is pretty experienced, and some of y'all might know quite a bit about antennas, and some of this might be old hat, and some of this might be a little bit of a refresher, and some of it might be at least a starter on some of the projects you might not have considered doing. So with that out of the way, I'll get started with some of the basics. So one of the things that I thought was really interesting about the first part of my job as an antenna design engineer was how to explain to someone that doesn't know antennas what makes an antenna bad, what really constitutes a bad antenna. Now, when you're designing antennas, of course, you want your frequency to be the frequency that you want, right? That's pretty obvious. One of the things that I feel that I used to make the mistake of making as an introductory ham or antenna designer was thinking that the highest gain is always the best, right? More gain, you know, best gain is the best. And that's not necessarily true. And one of the things, I think I gave this a version of this presentation, and I think you could have played a game with how many times I said, you're designing to the needs of your system, right? All you need to do is close the link. And that's ultimately the goal of anywhere, unless you're specifically designing for an antenna gain contest at the Microwave Update Conference or something like that. You really don't have to kill yourself to get the most gain out of an antenna possible. So that's something to keep in mind. And I advise a lot of students on rocket projects. It's typically aerospace engineering students that have no electrical engineering background, and they have to build the communications part of their system, and they have no idea what they're doing. You know, no offense to them, they just haven't been taught well, they haven't had someone with the experience, and so they get real confused too about that. You know, oh, the most gain is the best. But no, you really just need the closure link here. On polarization, one of the most interesting projects that I saw that really kind of changed how I thought about matching polarization is, and everything that I'll talk about is linked on the last slide with resources, but it's a guy, I forget his name, it might be something like Aaron, and he did a write-up of a project where he received circularly polarized satellite signals with a linearly polarized V antenna, V dipole. And some of you that are familiar, you might instantly be thinking, oh, that's a 3 dB loss from linear polarization to circular. That's terrible. That's a 3 dB loss. And he kind of pointed out, which is quite a bit of a theme of this presentation, if you can withstand 3 dB loss, it doesn't really matter if it's different, right? It's if you can still close that link to your system, then that's really all you need. So sometimes that can be an interesting way to get around something, is trying a different polarization than might be optimal if it's that much easier to design, or if it's just what you happen to have on hand. Now, of course, you can't be doing, horizontally polarized to vertically polarized, unless you're much more of a wizard than I am. But that's something else to keep in mind, right? Pattern, again, y'all probably already know this part, but some people get real focused on having a very directional pattern, because again, it tends to be tied to that gain, right? And something I've seen with students particularly is they want this really high gain, really directional antenna, I don't know, 15 element Yagi. They said, well, I'm going to point this at the rocket as it launches off, and this will be perfect. I'll have so much left over in my link budget. And this is the part where, if you could see me, I would hold my hand out as if I'm holding the Yagi, and I would turn around because I got distracted. Well, then what happens? You're not focused on where you need to be. Your directional antenna is useless if it's not pointed in the correct direction, right? So that sometimes is a trade-off there that you have to make of what's really useful for what you're doing. Bandwidth, that's just another consideration of how wide do you need it to be, how narrow do you need it to be. And that can take quite a bit of tuning if you're really tight on the requirements of what you're trying to do. And, if you really just need it for a single frequency, or if you're trying to do it over a wider band, that can take quite a bit of more tuning than some people initially think of. And I know I ran into that even professionally, of how much modification that can sometimes take. And then impedance match. And I know the first lesson we all learn, right, is impedance matches everything. You want a VISWAR of, 1.5 or lower, or else it's no good. You might as well just throw it out, right? It's worthless. One of the first programs that I worked did not have as much of a VISWAR requirement. It was a lot higher than that. And I said, well, how can this be? I asked my lead engineer, I said, isn't this important? And he said, well, actually, he said, you can have a great antenna with a crappy impedance match, and you can have a perfectly matched dummy load that doesn't radiate anything. And this goes back to, again, fulfilling the requirements of your system just to close the link. And I think one of your own hams has presented over this, Christopher Hamilton, KG5GAK. We tend to get into this sometimes trying to make a perfect antenna, and that can be a fun project, right? If you really have a lot of time to tune and you just want to play with it and learn. The point of this presentation is to show how much you can get away with, right? I think I see a lot of people that are new to ham radio, or hams that are just new to antenna design, have been a little intimidated about trying something sometimes, or else they try something and it doesn't work right off the bat. They say, oh, this didn't work, or I'm not good at it. It just takes tuning, right? And so for impedance match, you can have a poorly matched antenna that still gets the job done. And sometimes that's good enough for what you need, and it doesn't require you spending, hours and hours tuning, with VNA to try to get a perfect match. It'll still get the job done. Now, it won't be the most efficient thing, but sometimes, we can still have fun and not be perfectly efficient, right? So I'm going to talk a bit about 3D printing horn antennas. And so I just wanted to go over a refresher of what that is. So when I first in school looked at horn antennas, I thought if you'll see the image on this right-hand side of the screen here, the flared horn, the aperture part, I somehow thought that determined the frequency. And I had forgotten how wrong I was with that first impression until I gave a talk at a conference and didn't even think to mention it. And someone came up and they said, oh, well, if you change that, and they are pointing to the flared horn part, the aperture, and said, if you change that, it changes the frequency, right? And I said, oh, no. It's the waveguide dimensions, right? And that's back to our basic theory of waveguides, is that the dimensions are what's going to affect the frequency. Because really, even just an open waveguide itself is an antenna. And that's kind of the problem with antennas themselves, right? Sometimes you get antennas when you don't want them, and it's difficult to make the antennas that you do want. But that aperture flare is what affects your gain and your directivity, and your beam width. So that's just a basic theory thing to keep in mind of if you're going to start making modifications to your design, that's really what you need to be changing for different things. And the horn antennas that I'll show pictures of, I used a standard gain horn just because I wanted some standard dimensions. But of course, there's all kinds, right? There's conical, there's, E-plane, H-plane. You can go crazy with all the different kinds of horn antennas there are out there to play with. And here's just a picture of that horn radiation pattern, just in case you're not familiar with how directional it is and just how much gain that you can get from it, right? They're very high gain, high directional antennas. And, that's why we use them as medium gain antennas on spacecraft, on the programs that I work. So now I'll get into some of the 3D printing stuff that I did. So I found, and I'll go into this on the next slide, I found a write-up of how to 3D print an antenna and how to metallize it with metallic spray paint. And I decided I wanted to go to a space conference, and I wanted it to be funded as a student. And so I thought, well, how could you do this if you were in space in microgravity? And one of the things that I'll get into in a minute is how toxic some of that stuff could be. So I thought, well, if everything broke, what is the bare minimum of hacking something together, kind of with baling wire and duct tape kind of solution, and that you could still get an antenna to work. So that's what I'll be talking about here. It is not the most perfect designed antenna. It was something that I've had a lot of fun with and has been fun to get other people interested in it. But again, if you are a long-time antenna design engineer, you might not like just hacking stuff together for fun. So the write-up that I found was by Antenna Test Lab. And again, this link is in the back of the presentation for anyone that wants to look into it. And part of the problem with 3D printing, for anyone that's familiar with it, is that the PLA or the print tends to be a little rough. Particularly, this becomes a problem when you're getting into those microwave frequencies, right? I was looking at X-band, 10 to 12 gigahertz, and that's when the wavelength is small enough that diffraction becomes quite a problem, right? I know each band has their own issues, but diffraction is something that even professionals at those frequencies have to deal with. So what Antenna Test Lab did is they had to smooth that rough 3D print material, and they did it with something called dichloromethane, which is apparently so poisonous and toxic that it's not even being used in common paint stripper anymore. So that's when I had the idea that it probably wasn't something that you would use in a closed environment, and try to come up with another way to do that. And of course, if you were paying attention to the previous slide and notice what I covered the antennas with, you already know how I did that. But I'll get into that on the next slide. For those of you that are familiar with 3D printing, I use the real standard 3D printable model. This is a Google SketchUp graphic here that I played around with it in. I think it's for free, and I think OpenCAD is also another free one if you're interested in playing around with it. And it was just a 15 dBi standard gain horn. And if you don't know anything about 3D printing, all you need to know about the print technology and infill listed and the pattern is that it is the standard and cheapest settings, particularly for the infill percentage of 10%. And you might be wondering why I chose such a low percentage. Well, I was a student and I had to pay for the prints. And you pay by how dense the percentage is. So I went with the cheapest percentage. So I also was very lucky to have access to ANSYS High Frequency Structure Simulator. If any of you work RF or antennas professionally, you know that this is kind of the Rolls Royce of antenna design simulation software. But you can see here how the fields move through the waveguide if you're not familiar with it. And you can see this kind of return loss plot that you might expect for the simulation for these frequencies, for this design of antenna, for these dimensions. And if you're not familiar with return loss, that's just the S11, you know, kind of similar to the SWR. It's off. It's just a calculation from one to the other. It's the power put into port 1 that's reflected back and received at port 1, right? So this is a measure of how well matched the antenna is. And because this is sort of analogous to VisBar or SWR, you want this number to be low, right? So you can see we're in the, you know, negative 20 dB. So here are the S11 measurements of the 3D printed horn. And so if you can't see it too well, there are three lines here. I use one for aluminum tape, and that's this red solid line. I use copper tape, that's this dotted black line. And then just as a control, I measured the PLA itself, which is all over the place, right? And if you're familiar with VNA measurements, you know that seeing this repeated bump like that, that's usually not a great sign. So this, if you weren't looking too close at the PLA, you might think, oh, it's matched. But if you look closer and kind of know what you're looking at here, you can realize that it's pretty worthless. So I'm going to go back one slide so you can see that simulation again. See these two curves? Now let's look at the measured data again. See these two curves? So it's about similar to what you might expect. Now it's not as good, right? But we might expect that from a taped antenna as compared to a perfect simulation using, you know, a perfect electrical conductor. And one thing that I want to point out here, some of you who are old hats at this might notice, the copper tape has a worse return loss than the aluminum, which was surprising to both me and the professor when we looked at this, because, you know, copper is much more conductive than aluminum. So we thought, well, how on earth could that be? So I'll let you think on that. Some of you might already know the answer from those pictures. Let's look at the next slide. So, and then because we didn't have access to a full anechoic chamber, and if you do, I'm very jealous, and you can let me know. We did s.t.e.m measurements, which, you know, is just a transmission loss, kind of a, you know, cheap man's gain measurement almost. So you know, if you need to do this calculation, you do need to be in your far field, which is just a real simple calculation of 2 times the largest dimension squared over the wavelength. And here is where it's really obvious that that PLA only antenna is just worthless, right? So because this is a transmission loss, we want this number to be as high as possible on this graph. We want it to be, you know, not very much. And you can see here again, the aluminum tape outperforms this copper tape. So let's look closer at why that might be. Now remember I said these microwave frequencies, you have a problem with diffraction. So if you look and you can just see with naked eye, it's better in person if you can feel it, so you can see how much the difference is. But you can even see, look at how much smoother the walls of this aluminum tape are compared to this copper tape. And that was because we simply didn't have access to copper tape that was the same dimension as the aluminum. And it happened to be a lot thicker. So you have all these overlaps here that can lead to diffraction, and that can lead to your loss in your signal, right? And you can see the thickness here, it's over twice as thick. The aluminum was also a lot easier to work with. It was thinner, it was easier to kind of mold around corners and stuff. So that was something that I thought was real interesting to find out, is that, you know, I would have thought aluminum wouldn't have performed hardly very well at all compared to the copper. But again, it's to fulfill the requirements of that system, right? So if it'll do the job and it's easier to work with and it's cheaper, that is something that can get the job done for what you're wanting to do, instead of going out and buying copper tape, right? So another thing I want to mention, because some people express interest in 3D printing a circular polarization antenna. And this was a project that we had started, but were unable to test because I lost access to the test equipment for a bit and left the antenna there. But there are a lot of calculators for telling you how to do a helical antenna. This one pictured is just a right-hand circular polarization, and it's in the S-band, 5.8 gigs, and a little bit lower gain than that horn antenna at 10 dBi. So if you don't need as much gain and you want a circularly polarized signal, this would be a great project to do. You can circularly polarize a horn, you just have to feed it from 2 different ports, and it can be a little difficult. If you are going to try this project, and I have, again, the links in the back of the presentation, we had difficulty because you are printing something that's long and flat, kind of like a ruler. When you pull it off the 3D printer bed, it has a tendency to bend and warp. So anything like this, you have to kind of use caution scraping it off the 3D printer there. And this would be something, if you remember, for the 3D printed horns, I used a real low infill. Well, that's a real sturdy design, right? So you can kind of get away with that. If you're going to be using a flimsier design, you want to use a lot higher infill to try to make that a little bit sturdier and be a little more careful when you're pulling it up. So with that, I know there was a request to talk about some of the stuff with SETI, and this has been an ongoing project, and for any of you that are interested, there's a lot of resources and a lot of ways to get into this. So in May of 2019, I followed the software-defined radio open source platform called GNU Radio on social media channels, and they posted that they wanted to have a hackathon with UC Berkeley SETI out there in California. And I thought that sounded like the coolest thing I'd ever heard. You end up going, this is the Allen Telescope Array. They're in Hatts Creek Observatory in the absolute middle of nowhere, California. There's nothing but fields and mosquitoes out there. And so this is also sponsored by Breakthrough Listen, which is a prize competition to try to hear signals, intelligent signals in the universe. And so they did this open call for RF professionals. They had machine learning experts and people within that GNU Radio open source community for a 3-day hackathon there at the ATA. And I think, not entirely sure, I wasn't the only ham, but I was the only one that was going to be doing antenna design. There were a lot of machine learning people and a lot of software people, really. But they came up with several goals that they wanted to do at this hackathon. They wanted to detect and characterize radio signals and using deep learning approaches, data capture and management and quality assessment for the radio systems. They've got a real neat radio room in there with all kinds of stuff going on. The part of the effort that I worked on was the RF front end and the antenna status and health management and assessment, trying to easily look at, remotely, is something off with one of the antennas in the array? What part of it is off? How would you monitor that? How could you be notified of that remotely? Because again, it's in the middle of nowhere, right? So it would be nice for someone who's not staying there on the campus to be able to be alerted and have something to fix. And then there was the new radio-based tools for both real-time and offline processing there at the ATA, and they've really further developed that capability, and there's a whole, I think, ATA block subset that they've created since then. And there's a lot of other stuff with SIG-MF and transitioning to these open source signal data formats that I did not fully understand what they were doing. If you're a software person or IT, you probably understand that a lot more than I do. And mostly they were really interested in getting a really open and collaborative space for everyone to solve problems, because that's part of Breakthrough Listen and part of the open source community. So as a bit of a background about the ATA, they have 42 telescopes there. They want to grow to over 350, but as with anything else in space and science, funding is a problem. It's been there since October 2007, and it was the first of its kind for this large number of antennas, but small diameter centimeter wave interferometers. So I know they look like, I think someone called them cans of baked bean stacked on a satellite dish, but they're actually pretty interesting antennas. I think I have a photo. Oh, this is the log periodic dipole array that they have inside. This is the thing that looks like a can of baked beans on that dish. And it's cryogenically cooled to reduce the noise, because of course when you need really high performance, the heat starts becoming a problem, right? And it was really interesting to get to crawl up in there and get to see this kind of stuff. But this was also something that can go wrong, right? The more advanced your system is, the more advanced your electronics. Once you start introducing cryogenic cooling, that can be an issue, right? If the fridge goes out, your antenna isn't working so well. So a bit more about those log periodics. They had 2 antennas in there, if you saw it, and that's for the dual polarization. And they're expanding. I think they had not quite finished improving all the antennas to go from, originally it was 0.5 to 11.2 gigs, and they were trying to go all the way up to 18. And one of the things that I thought was really interesting is there wasn't really any point in going to a wider bandwidth, because they couldn't find an LNA, a low noise amplifier, to match that range, right? Let's see, go on. So a lot of the issues that we encountered out there, they're mostly mechanical. Again, with the cryo breaking, they had the same issues with circuit boards and soldering breaking that, you and I might have. They had hot and cold loading difficulties, trying to get the, antennas the right temperature. And they had a lot of, connector issues. Half the time it's always the connector, right, in anything that we do. And they had a lot of mismatched feed styles. Like I said, they had gone up and upgraded to try to cover over a wide bandwidth. And that was creating some issues for them. So for the group that I worked with, Derek is with GNU Radio. He's a PhD student out at Cardiff University, really brilliant guy. Katie Frey works for Harvard and Smithsonian Library at the Center for Astrophysics. And Michelle Thompson is with the Open Research Institute. She's also a ham radio operator and excellent knowledge of 3D printing antennas for microwave, if any of you are aware of her. And so what we wanted to do was kind of combine all this sensor input and kind of fuse it together for multi-sensor data fusion, kind of a one-stop shop for the operator to see what was going on, right? They had some code that was even worse than what I would write that needed to be cleaned up. And there was talk of, and which is now finished, the new radio processing block specifically for the ATA. So, and here's an example of some of that antenna health data that I've talked about. You can see here, looking at the cryo temp, you know, and looking at the range of whether or not it's performing nominally, a little low, a little high, or wildly out of range. So that's about all I have. I do want to mention the resources and links that I talked about. There's that B-dipole antenna is the mismatch polarization experiment that I talked about. That's a good write-up of that. The resources of the horn antennas that I showed. If you're interested in the 3D printing your antennas, Antenna Test Lab has a great write-up of step-by-step of how to do it, and they even have STL files, so you don't have to create your own horn within CAD software. The print for that helical antenna frame that I mentioned, and if you're in need of a calculator for how to design helical antenna, I've also linked that in here. There's an overview of the Allen Telescope Array by SETI. Dr. Steve Croft is a head guy out there. There's a write-up of the hackathon that he did last year. There was going to be a second hackathon this year, but of course COVID got in the way of it, just like everything else. And if you do have any interest in the software-defined radio, if you haven't looked into GRCon, the conference for GNU Radio every year, it was virtual this year. They've published everything to YouTube, and the particular link is Steve's talk. He's a really, really great speaker. Really just loves to engage public and talk about what he's doing. And I think now they've even posted links to some of the workshops that they had done during the GNU Radio conference, which you needed to pay for to learn in real time. So there's some really cool resources there on the GRCon YouTube, if any of you have any interest in working with that. So with that, just to wrap up, I know antennas can be difficult. I've dealt with some hams or people just getting introduced to it that feel ashamed for buying one. My manager who oversaw 150 antenna design engineers is a ham, and he was talking to me about some project he did, and he mentioned that he bought an antenna. And I said, "You bought one?" I said, "After all you know about, you know, designing one for yourself and all the resources you have?" And he waved his hand at me and he said, "Who cares?" He said, "You can buy one for, you know, X amount of dollars." He said, "It's not that big a deal." But I say that just because there are always some people that get intimidated, right? People new to it. Again, if you are old hat or Elmer at this, you might be thinking, "Oh, well, I'd never be intimidated of an antenna." But there are other people more junior that they get a little nervous about it. If you're going to be messing with the microwave frequencies, you know, diffraction can be a problem. We all know, particularly in electrical engineering, that the connector is always the problem. Of course, not always, but it's always one of the first things that we should check. Even if you're trying to listen for intelligent signals from space at the Allen Telescope Array, right? And last things are, even I, as an antenna design engineer for a major company, we had to tune and tune and tune, right, to get things to where we needed to be. So there's certainly no shame in, having to do that in your own projects. And lastly, I personally think antennas can be a lot of fun. I enjoy talking about them, enjoy playing with them, enjoy working with them for a living. So with that, I'll wrap up and take any questions.
Well, we have your links there. We have access to those, or Jeff, do you have those?
Yeah, there's a link I put in the chat to the presentation slide deck.
Okay, any questions for Karen?
Karen, I thought that was really interesting. I really appreciate it. Great presentation.
Very, very interesting. It's a lot of that would fit into, in ham radio, guys that are interested in the, the 10 gig and above, I guess is what it's usually called. That would be it really fitting for that. That's for sure.
And Bill N0LAJ put a great comment in the chat. Karen, you might want to read that.
Oh, thank you. Yeah, the practical approach, and hams are usually pretty good at this, right? More so than, say, university professors. I was very lucky to have a ham as a professor, but they tend to teach you the perfect theory way to do things, right? Instead of actually getting out and putting some together and having some fun with it. I grew up on a ranch, and sometimes you just gotta fix something and wrap baling wire around with it, and it can be a little bit more fun. So usually hams are pretty good about that.
Yeah, I thought your comments were interesting, Karen, about the, you don't always have to have the best the best gain and all that, because a lot of times that's part of, like in like voting systems and things like that, you may not want to have a tremendous gain. You may want them to be a little bit deaf, and as part of the design. So that's an interesting comment to me. Well, anybody else?
What's the cost of 3D printing?
You mean, so the initial cost, 3D printers have come down quite a bit. There are decent and popular models under $300. And then, so that's just your initial cost. The PLA, is pretty minor, just a few bucks here and there. They also make, conductive filament that you can print with that would be, fun to play around with. It's more expensive than the regular PLA, right? I couldn't happen to get my hands on any of it, but that would be real fun. And one thing I do want to mention real quick, because some of y'all might have boats. I am not a boat person, but someone said that boat epoxy, that they make a conductive version that would also be a fun way of metallizing stuff. But yeah, so you can spend a lot of money on a 3D printer, but they make decent ones under $300.
Okay, anybody else got a question?
Can you rent time on a 3D printer?
Well, you could, or you used to be able to. That's what, if you've heard of a makerspace, I know a lot of you hams probably have garages filled to the brim with equipment. But for some of us folks in tiny apartments, what they had is maker spaces that you could go and pay a membership for, and they would have, woodworking equipment and 3D printers and stuff like that. Yeah, I see you're looking it up now. And you could just rent time and bring in a file and 3D print it right there, and that's all you needed them for. And also people at those places would tell you, they'd help you and have classes and stuff. And that's how I would have recommended to do it before. Now, I don't know about nowadays if they're still open or surviving or what they're doing.
Looks like Jeff's got a couple of them there that look like they're.
Looks like COVID's probably got them shut down right now.
Yeah, like everything.
Oh, and someone put the chat for the Denver library. That's how I did it at the university. It was through the library. So yeah, they can also be an affordable option. When I did it as a university student, I think it was between $5 and $10 to print each horn. So not a big deal. But if you're a broke student, it adds up.
Okay, last call. Anybody? Any final comments?
My question is Jerry, W0FFC.
Yeah.
Could you talk a little bit more about SETI and what they're doing and how they analyze their data? And because it's been around, 13 years now. And so where are they and what kind of things are they looking at?
So SETI they've really expanded a lot. They've got all kinds of scientists that work for them now. And so there's the SETI Institute, and then there's UC Berkeley SETI. And I am not an expert on how that separates within the university system and within the institute, but UC Berkeley SETI has partnered with GNU Radio in order to incorporate more of an open source approach in their data. So they do some listening projects, right, as you might imagine, but then they do a lot of astronomy, radio astronomy work out there, just the standard stuff. And that's most of it that goes on out there. I think some people, they hear SETI and they think it's all woo-woo searching for aliens, but they do a lot of very standard astronomy projects out there as well.
Just to comment, this K0TOR, Jim Beal. Karen, I got to agree with you as far as it can be frustrating. I enjoy antenna design, trying to see how I can come up with a better design and fit it in a smaller space. I'm not up to high frequency stuff like you're working, but it can be really frustrating. I can work and try to get a design that I think is going to work well, try and get it squeezed in the amount of property that I have. And somebody else can come out with a coax and hook it up the ring gutter and seem to work better than what I got. So I can appreciate what you say as far as the frustration, and just stick with it and see if you can figure out where the problems are at and work around them. But it's been very challenging and very interesting. So I truly enjoy it.
That's great. Yeah, it's so I'm in grad school right now taking antenna design, and the professor is, he's a university professor interested in research more so than actual design and hands-on, but he even has continually said it can be real easy to make a dipole where you don't want to, right? Even in a board design and everything like that. He said, so you would think it wouldn't be hard to make the antenna that you want when it's so easy to make antennas that you don't want, but it's frustrating for everybody. Even there's no telling how long he's been at it. So yeah.
Well, I do appreciate your presentation, so thank you.
Okay, any final comments? We'll close it out here. It's about 10 till 8. Again, Karen, thank you very much taking your time to do this, and very interesting, something a little different than we're used to, which is really, really good. And again, thank you very much. Maybe we can call on you again sometime.
Yeah, absolutely. Thank you all so much for having me and listening, and any questions, of course, just reach out and let me know. And
you're sure welcome to join us here on the Denver Radio Club, our presentation. Someday we'll get back to real meetings face to face, but you're sure welcome on the third Wednesday to join up and just participate and listen to what programs we have. We think we have pretty interesting programs, just like yours is very, very interesting. So the invitation's always open to, if you got the time to come visit.
Yeah, absolutely. Thank you so much.
All right. Well, good night. And I guess everybody, unless there's something for me or any other comments, we'll close it out here. And thanks everybody for attending tonight. Hope it enjoyed it as much as I did. 7-3.